Let's talk about circularly linked lists. Let's start with what are they, okay? So here's a singly linked list, right? You have this head pointer. Right, and what is that? It's an address. I always put an @ sign for a variable that's a pointer. I always draw like that. And maybe it points to the first element in the list. Say that's A, and then we have a B over here. Next one might be C. And then we have another one, a D over here. Okay, there's a singly linked list. The one on the end of the list here would go to null, all right? If we have a doubly linked list, looks like this. Points to the end of the list, then previous, right? Previous, and the previous pointer from here would go to null, right? There's a doubly linked list. So what's the difference between either of these and a circularly linked list? Well, since I have a doubly linked list in front of me right now, let's change this into a doubly linked list that is circular, all right? The only difference is this doesn't go to ground here. It goes back around and points to the first. And the backwards pointer no longer goes to ground. Null, we'd say. I'll draw this one up here so it doesn't get too ugly. Goes to the end. Okay? So, what happens when we traverse this? We traverse it in the exact same way we did all the other kinds of lists, right? So, if we want to go forward, we start at the head node when we say, okay, I'm at A. Go to the next one. I follow the next pointer. I'm at B. Go to the next one. I'm now at C. Go to the next one. I'm at D. Go to the next one. Well, he no longer points to null, so he comes back around here to A. B, C, D, A, B, C, D, A, B, C, D. You just go round and around and around. It is a circularly linked list, okay? Now, if this was only a singly linked list, there would only be the forward pointers and this circle over here. In a circularly linked, doubly linked list, it would be the same thing in the backwards order at the same time. So I start at the tail and I go previous. I can visit all these nodes. I go previous, and I end up back here at the end, all right? So just going to go around and around and around the other way. That's all there is to a circularly linked list. Now, why you might need to use one, that depends on the applications that you're working on. Off the top of my head right here, the times I've used these is when I was writing a scheduling system. And I needed to do some work. Each unit of work is a node in this linked list. And I needed to share the compute time across all the jobs that the machine was doing. So I would have to work a little while on A, and then after a certain amount of time, I would move to the next thingy in the list of tasks to deal with. And then I would do some work on B, and after some time, I'd move on to C. After some time, I'd move on to D. After some time, I'd say, what else should I do next? Go back to A. And we just evenly distribute work around to all these tasks all day long until one of them dies, and it would then be removed from the linked list, and then it might just be ABD, all right? So I hope that's an example that we can easily relate to give meaning to why we would ever want to do such a thing. Now, how do you create a circularly linked list in a C++ app, right? Well, they have a list class that's a doubly linked list, right? So if you look through down here, it says this is implemented usually as a doubly linked list. It depends on how the library in your compiler was built, right? Now, if you want to use a circularly linked list, you want to make one out of the doubly linked list, you can either, create a new template class wrapper, which would be a really great way to do this. That way it would handle any kind of element types and so on. You'd be extending then the standard template library here. But before you go that far, let's just hard code one and go over the basics, right? You can then convert that to a template. I'll leave that as a task for the student, okay? Now, what do we know about the regular old standard list, right? Well, we know we have these iterators, and that's what I was just showing you on the paper. You're going to start at the beginning of the list. You go along until you run into the end. And once you get to the end, you have to go back to the beginning. Well, we can just write code that literally does that, right, in a nice program. So let's first start out by saying, I want a list of some user-defined data type. I'm going to call this foo, and I'll show you the class in a second. Let's start with this. I'm going to insert things onto the end of the list that I just created right here, okay? So each one of the things is right here, right? These are the things I'm going to put into this list. And by appending each one of them to the end of the list, they're going to go into the list in the order you see them here, okay? Obviously, if I said list.begin here, it would put this one before the current element at the beginning of the list. And this one before that, effectively inserting these backwards, all right? You can do it either way, but just so that we got our bearings here. I'm going to fill the list with some items, and then I'm going to print out those items, okay? Using the range-based for loop, and I'm going to print them out like this. Now, if this was a list of integers, this would be fine, but it's not. It's a list of foo objects, all right? So the values that go in the list are constructed right here. Give me a foo, and these are the arguments to the constructor. So let's look at this foo class up here. Now, I do this because I want you to see a more realistic example than just a list of integers, right? And if you actually put anything real in a linked list, you're going to have to deal with some of the extra responsibilities. Okay, so one of the responsibilities is that we're going to create a foo object. We need to have a constructor to make it convenient to create these things so we can put them in our list. So I'm going to say what? This is a foo. It's got private name and value, member variables. Constructor takes the string and an int, and it's going to take the string and set the name to the string and the value to the integer that's passed in, all right? Then what's this all about? This is an overloaded operator to create a function, but knows how to use the insertion operator when writing into the output stream in order to print an element of type foo. And what does it do? It's going to print the name equals value, these two fields from our foo class whenever anybody tries to print one of these things, right? So that's what's happening down here, right? So if I go down here and I look at what's happening, I say auto give me a reference to the elements in the list, okay? So one at a time, I will be a reference to one of the foo elements that are in this list, and I need to be able to print them to standard output or cout. Okay, and of course cout does not know what a foo is nor how to print it, so that's why we put this overloaded operator in there. So let's go ahead and compile this and run it. See what it does. Well, that's not shocking. I put first one, second one, third one, fourth one, and so on, seventh one in my list. There's the names, and these are the values that we saw when we were writing the code, first, second, third, fourth, so they're in order by their names that I used to put them in my linked list, and some other payload data, all right? Okay, just so we know, remember how a regular list class works, all right? So let's look at this version now. Let's see what happens in here. Absolutely no changes here, okay? Let's see what's happening down here. What are we doing? Wow, we got command line arguments going on here and all this other stuff. So what I decided to do is I got an optional command line argument called count. So when I run this program, I can change the value of this thing. The default value is going to be 10. And what do I got here? I got an n colon, so that means if I have a command line argument that's n followed by a value, there's my usage statement down here. It's square brackets, means it's optional because I'm overriding, I should say, the default. If I specify it, if I don't specify it at all, count will be 10 by the time this code here ends. And the way I assign the value to count is I do it like this. All right, this may not be super obvious if you've never seen this before. What I've done is I've created an object of type iStringStream. This creates a stream, which looks like cin, right? All these streams, like cin and cout, right? This one creates a stream from a string, all right? Remember, opt-arg is the thing from getOpt that is a string, that is the value for this argument on the command line. So if I create a stream out of it, this whole thing looks exactly the same kind of object as like cin double right count, right? I want to write a program where I can just say, run the thing minus n72, rather than running it and then having to type in 72 and blah, 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 blah. It's easier to script things if you use command line arguments rather than having some interactive thing with a terminal, all right? Almost all real apps, if you've ever thought about it, use command line arguments. They don't have a dialogue with a user. That's just too annoying to script, all right? So this is what I've decided to do to provide an optional argument. Now, this doesn't have anything to do with circularly linked lists. I'm just pointing it out so that when we run this program, we can vary the count value. That's why I put all that in there, all right? So up here, no changes to this code at all, just print them out. Then we got some interesting thing going on down here. This is how I make a circularly linked list out of a regular standard list, which, as we know, is a doubly linked list. So I'm going to print out I'm circularly visiting this many elements, right? So if I don't specify anything, we know that will be 10. So if I say list size is greater than 0, I'm going to do something in here. Otherwise, I'm going to do nothing at all, right? Now, this code down here would most likely fail if I didn't do this up here first. Right? Well, what happened if this list was 0? Well, would this work? Yes, it would. This would return list.end to signify that there is nothing in the list. If I then went into this loop and I eventually came down and did this, this right here would fail, right? Because I'm trying to print something that does not exist. All right, so first make sure there's something to print before you print it. That's what this is doing. All right, let's look closely at what's happening down here. Okay, so what do I want to do? I want to circularly visit all the elements, count number of times. Well, let's go back up here real quick. How many are these? There's only 7 items in my linked list. So if I take the default, it's going to want to print 10 things. That'll be all 7 of them. And then I want to see the first 3 again, because I had to go around and revisit those first 3 in order to satisfy the printing of 10 elements. All right? Big picture here first. Okay, so how am I going to do that? I'm going to say 0, I is 0, and while I is less than count, add 1 to I. So this is going to allow this loop to run 10 times. I created an iterator that points to the first element in the linked list just to start things off, all right? So the first time through this loop, it's going to say, print out the first item in the list. And then put a carriage return, and then what happens down here? I'm going to add 1 to the iterator. That points it to the next list, or the next element, rather, in the list. After I've incremented this, right, it's a pre-increment, I'm going to ask, did I just increment it to the end? Well, that's the case. I got to go back to the beginning of the list. So if I run off the end of the list, just simply set it back to the beginning of the list. Go back up to the top. Print it out again. Go around and around and around and around and around here 10 times. What if I did not run into the end of the list, right? So in this example, we know there's 7 items in there, right? So it's going to print the first one the first time through the loop. And it's going to add 1 to the iterator, which makes it point to this second element in the linked list. And it's going to ask, is it the end? The answer is no. So it falls off of there and comes back up the top. Did I print all 10 yet? No. Print out the second element, all right? So this is how I can visit a regular old standard template library list in a circular fashion, all right? But really, that's really all there is to it. Let's go ahead and compile this up and run it and see what happens. So here we go. Here's me dumping out all 7 elements just to make sure that my brain works, that I can actually just visit them all, right? This was the range-based for loop there. Now I want to say circularly visiting 10 elements. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 7 we know was the last one that was in the list up here, the 7th one. And we know the first, second, and third are called first one, second one, third one. Okay? And we print out the values as we go. The values are simply baggage to make this interesting. In fact, the entire value of the elements are just baggage as far as the traversal logic is concerned. But what we've seen here is a couple of nice items, right? This is an arbitrary class now, not just, I want to print out integers. No, this is actually starting to take form of a realistic business object that could be of some value, okay? By the way, if you want to use the in string stream, that's in this header right here, by the way, right? This S stream, that's where this thing is defined. All right, I forgot to mention that a minute ago. And what else is interesting about this? I think that's about it. You just have to keep track of whether you run off the end of the list and wrap the thing back around again. All right, so let's go ahead and run it again. Minus n. 2. All right. I only want to visit 2 in circular order. Well, that makes sense. I didn't even get all the way around once. What happens if I go 4? Same thing. Didn't even go around once, but I did visit 4 elements. What if I want to visit, 14, right? Well, now it's going to go from 1st through 7th and 1st through 7th the second time. What if I want to go to 15, right? These are kind of like the edge cases, right? It'd be nice to make sure it doesn't screw up if you just, come out with an exact match of however many elements, right? So 14 worked perfectly because it ended exactly at the end of the list the second time it reached it, right? 15 worked perfectly. It ran through the whole list once, then it ran through the whole list a second time, 7 each one, and then it ended on the first one, right? Well, what if I go to maybe 13, right? That'd be one whole pass through it the first time and not quite a whole pass through it the second time. There's the first one. Here's almost all of the second one. So these weird cases are working, right? What if I say n equals 1? That works. What if I say n equals 0? It works as well, right? So let's say we made the high and mighty crime of forgetting to check if the linked list was empty first, all right? So what's this going to do? Well, the reality is I have no idea, because what we're doing is we're dereferencing the end element in the standard list library, okay? And if we look in here and we look at what it means, okay, this is the end element, returns an iterator to the thing that follows the last element of the list. There's a nice little picture here, okay? This acts as a placeholder. Attempting to access it results in undefined behavior. So anything could happen, right? If I run this program right now, if I'm lucky, someone will bring me a hamburger. I don't know. In theory, that could happen because this is undefined. That is very unlikely to be the result of running this program, all right? But like I said, anything could happen, probably limited to my program crashing or something like that, okay? We've seen this before. All right, so with this thing gone, right, what did I say? It would fail if the list, in fact, was empty, because this is asking what the list size is. It's not asking me how many I want to print. It's asking me how much is actually in the list. And since the list is not empty, that code would work okay anyway. But if I comment this out, what will happen? Well, will this work okay? Actually, yes, it will, because a range-based for loop handles the empty case. It simply will never execute the body of that loop. I am very confident this goes going to be okay. Well, what about this guy down here, right? As we said before, if you don't check to see if there's anything in the list, and I say, oh, I want to print 10 elements. Well, it's going to go grab the reference to the beginning. This will be satisfied, and it'll try to print out that value of the first element, which does not exist. So we don't know what's going to happen, right? So let's see here. And I got a segfault. Well, let's see what Valgrind has to say about it. So Valgrind comes along. Look at all that, okay? So it says, okay, I want to visit. Well, first of all, it prints out, hey, here's all 0 list elements. Like I said, the range-based for loop is okay. It didn't execute the body. But the loop we wrote, because I removed the check, does a foolish thing, and it tries to start dereferencing non-existent elements. So what happens here? It says a conditional jump or move depends on uninitialized values. At this address in this OStream thing, maybe you don't really know, maybe you don't recognize the fact that basic OStream is another word for cout, right? Well, it goes along and it says, oh, I'm trying to execute the insertion operator while doing this on line 22 of this program. And if we look there, I'm sure, very confident that that's the body of the for loop, right? So what happens down here? It says some more stuff about the same problem. And on and on and on. It goes on over and over and over. Complains a lot. It says I'm trying to use 8 bytes of something. Turns out that 8 bytes, most likely, I'm sure it is the value of the pointer in the head pointer of the linked list, which is pointing, at the end object, which doesn't exist. So the code logic is just plain broken. What else is happening here? Blah, blah, blah. A lot of complaining about line 22, 22, 22, 22, 22. So you'd be a fool to think the problem was anything other than line 22. Now look what happens over here. It actually prints out nothing equals 0 many, many times. That's interesting. So Valgrind ran, and it actually, if you count these, I'll bet there's 10 of these, okay? You could say, well, yeah, my program worked fine. It's not leaking any memory. I allocated 2 things and freed them back up. And I watched your great video on Valgrind, and you said that everything's fine here. Well, everything is fine in terms of allocating and deleting memory. But it's not fine in terms of using the memory that's actually in the system. It just so happens that we're not touching non-existent memory addresses when this code runs. Right? You got to think about what this means. We're touching whatever data is in memory where this end thing is, right? The iterator is pointing to end, and now we're on the dependent on how the library was created, okay? So what does it mean to do this when IT equals end? It's completely up to the library. This library, I suspect, actually has an object somewhere inside a memory that does officially represent this end thing. Because if you think about it, I'm doing a comparison operation here. In order for this to work, the compiler needs to know some scalar numeric value is equal to some other scalar numeric value in order to do this comparison. Ultimately, deep down inside, that's what really is happening. So there's probably actually an object somewhere that says I'm the official end, and it actually is in memory, and it actually has garbage values, okay? Therefore, when I do this up here, that garbage is what's being printed. If the library was written in some other way, where the end was actually like the null macro, like in C, or a null PTR, whose value is 0, and I dereference 0, then I would end up with a segfault, and Valgrind would say, that wouldn't work at all. It would never print out these things. All right, so when I run it like this, and it just simply says, I'm visiting 10 elements and I dump core, you'll notice I don't get the 10 elements printed out. When I run it with Valgrind, it actually works better. Okay? Why is that, you suppose, right? Why would there be an end object somewhere that's actually in the valid range of addresses when I run it with Valgrind, and it's not when I run it without? Either way, it's broken, right? And Valgrind can tell you it's broken, and exactly right there is why. Okay? Now, the reason is that when Valgrind runs your program, it has to keep track of everything that's going on. Your memory, what I like to call the memory footprint of your program when it runs with Valgrind, is different. It's bigger. There's a lot more stuff in memory when Valgrind is running. Okay, and sheer, law of large numbers, the law of averages says that if there's more stuff in memory and you're dealing with a wild pointer, then there's a more likelihood of getting garbage from that pointer, right? So if your address space is just full of more memory, the odds of finding something go up. That's really all it's about. It may also be that the way Valgrind itself is designed, that everything, no matter what it is moved into a memory location so Valgrind can watch the memory interactions take place. This is an open source thing. Feel free to, if you're interested in that sort of thing, go download the source code and figure out how this thing works. It's actually going to be pretty cool. You're going to get totally into tons of operating system stuff and process tracing and memory management and all this other crazy stuff. And you'll see how it figures out what's going on, right? I mean, you think about this. How in the world can one program know what's going on in a different program and monitor every time it reads and writes from memory to say, oh, that doesn't look good to me, and print out a nice little error like this, right? This is a non-trivial app, okay? All right, so let's go back and look at CL2, line 22, to make sure it tells us exactly where it died. Yes, it died right there, okay? Why didn't it die down here? It did die down here, right? What does it mean to print a foo to see out? Cout doesn't know how to print that thing. It doesn't know anything about it. So it has to use this overloaded operator up here to do the printing. So this is the line of code that actually was doing the printing, which is on line 22. I'll move my cursor back up there. Line 22 is where the problem is. All right, so Valgrind is definitely our friend. Okay, so that's what happens if you don't do it right. Okay. And here's what happens if you do it right. All right, Valgrind, no complaints. This is a correctly running program. All right. Anyway, I think I beat this thing enough. That's how circularly linked lists can be built out of regular old C++ standard list templates. Thanks for watching. See you next time.